Next classification what we have to see is stable and unstable systems. Okay. Still we are in the classification of systems. Stable and unstable systems. Unstable systems. Okay. Try to understand what is a stable system, what is an unstable system. Before understanding this, we are having only one stability criteria called as Bibo stability. B-I-B-O stability. So what do you mean by that? Bibo stability. B-I-B-O stability. That means bounded input, bounded output stability. Bounded output stability. What is that supposed to mean? Suppose if a bounded input is given, then we have to get the output which is nothing but bounded. Then we can say the system is stable. If for a bounded input, if the system is giving you unbounded output, then we can call the system is unstable system. So this is nothing, this is the only criteria. Don't think about anything. Suppose, sir, what if it is a unbounded signal? Again, I can get unbounded signal output. So then can you call this a stable system? No, no, no. There is no such criteria. We have to check for bounded inputs only. That means if input is bounded, then we have to check the output, whether it is a bounded or unbounded signal. So if input is bounded, output is also bounded, then we can call the system is a bounded input, bounded output, stable system. In simple, stable system. Next, suppose if the system is unstable, then we have to see if the signal is bounded, input is bounded, then the output must be unbounded. Then you can say the system is unstable. That's what the meaning of it. So here, stability means if input is bounded, mathematically how we can show a signal is bounded? Mod x of t must be less than or equal to some maximum value which is less than infinity. That value will never go to infinity. Then output is also bounded. That means mod y of t must be less than or equal to some maximum value n, which is also less than infinity. That means that is also bounded. Then we can call the system is a stable system. Then we can call the system is stable system. That's what the meaning of it. Okay, take it. For bounded inputs, we have to get the bounded outputs. You might remember some signals which are bounded signals, some are unbounded signals. Let's say delta t, bounded or unbounded, which is unbounded because its amplitude is tending to infinity at t is equal to 0. U of t, bounded, R of t, unbounded. Let's say delta n, bounded, delta n, bounded. Next, suppose if I say u of n, these are bounded. E power minus at, unbounded, because at t is equal to minus infinity, this value goes to infinity, unbounded. E power at, that is also unbounded. E power minus at u of t, bounded. E power minus at u of minus t, unbounded. E power at u of t, unbounded. E power at u of minus t, that is bounded. So these exponentials, for all of them, a is positive. If a is positive, these are nothing but bounded, unbounded. If a is negative, they will get reversed. Okay, take it. So just make you understand what is a bounded, what is unbounded. So once we understand this, then we can understand what is a stability. That means whether the input is stable, whether the input is bounded, then what will happen to the output? So if for input is bounded, then output has to be bounded. Then we can say the system is stable. Let's take some examples and you have to see whether the system is stable or not. A system is represented like this: y of t is equal to x of t square. We have to check whether the system is stable or not. Here the system is stable. How, sir? See, don't think it is a parabola or something like that. We don't have to see like that. What we have to see is, if input is bounded, then what will happen to the output? That's what the only we have to check. If input is bounded, what will happen to the output? Now, input is bounded means, can I say it is some finite value? It is some finite value, square. So if you take a finite value and square it, whatever may be the large, it doesn't matter, but still it is going to be finite value. It will never reach infinity. Maybe it is going to be a large value, but still it is going to be a finite value. So it is finite. So I can say for a finite input, we are getting finite output. So the system is stable system. Stable system. Next. Y of n is equal to e power x of n. We have to check this, whether it is stable or not. Again we will say, if input is finite value, then what will happen to the output? So it is going to be e power some finite value. This is the only we have to check, finite value. Then e power finite value, if you take e power 4, e power 5 like that, so still it may be a large value, but still it is going to be a finite value. So again it is a finite value. Then the system is stable again. Then the system is stable again. Y of t is equal to x of 2t. See here, what the system is doing, if input is given, we are getting x of 2t. X of t input, output is x of 2t. That means the signal got compressed. So if the signal get compressed, what will happen to amplitude? It will never change. Amplitude will never change in the time compression. Only the width of the signal will change. So I can say this system does not change the amplitude. That means amplitude does not change. Amplitude does not change. That means finite amplitude is going to give you finite amplitude only. So I can say the system is stable. The system is stable. Next, y of t is equal to cos omega naught t into x of t. What kind of system it is? Is it a stable system or not? Again, it is a stable system. Why? If x of t is a finite value, what about cos omega naught t? Is it going to be finite value or infinite value? It's always finite value, because cos function is always varying between -1 and +1. Its value will never go to infinity. So it is a finite value multiplied with again a finite value. So the result is also a finite value. Then we can say the system is stable again. For finite input, we are getting finite output only. The system is stable. Next, y of t is equal to x of t by t minus 4. Is the system stable or unstable. Let's see. Let's take x of t is a finite value. Let x of t is equal to some k, which is finite value. Then let's check it out, y of t. Y of t is equal to k by t minus 4. So it is an unbounded function. Why? Because at t is equal to 4, y of 4, what is the value? K by 0, which is nothing but infinity. That means if x of t is a finite value, but at a particular instant y of t goes to infinity, that means unbounded function it is. So I can say for a bounded input we are getting unbounded output. The system becomes unstable. The system becomes unstable. That's what the meaning of it. Okay, take it. Y of t is equal to sine of x of t. Now, so it doesn't matter what is the input, always the sign value is between -1 and +1. Sign value always bounded by. So if you take whatever may be the input, it doesn't matter, sign function is going to give you a finite value. So if x of t is finite, again y of t is also finite. So remember, sign function is always bounded, is always bounded. Bounded between -1 and +1. -1 and +1. So the system is stable again. The system is stable. Next example. Y of t is equal to running integral -infinity to t x of tau d tau. Running integral x of tau d tau. So we have to see whether it is a stable system or unstable system. It is an unstable system. Why is that? Let's take one example you can understand easily. Suppose let x of t is equal to u of t. So you tell me, u of t, is it a bounded signal or not? Yes, u of t maximum value is equal to 1. So I can say it is a bounded signal. So it is a bounded input. It is a bounded input. Then what is the output? Y of t. Then output y of t is equal to running integral u of tau d tau. We know this running integral of step function is a ramp function, and a ramp function is a unbounded output. So I can say for a bounded input u of t, we are getting unbounded output r of t. So the system becomes unstable. For bounded input, we are getting unbounded output. The system is unstable. Okay. Next, y of t is equal to dx of t by dt. Dx of t by dt. This is also unstable. Let's take the same example. Let x of t is equal to u of t. So we know it is a bounded input. Bounded input. Then what is y of t? y of t is equal to du of t by dt. Du of t by dt, differentiation of step function is delta t. Delta t. So we know delta t is a unbounded output. So for a bounded input, we are getting unbounded output. Then the system becomes unstable. Okay, take it. Suppose it is given y of t is equal to integral t to t plus 2 x of tau d tau. You tell me whether it is a stable system or unstable system. The answer is a stable system. You may get doubt, sir, here the integration you said is an unstable system, but here also the integration, but you are saying stable system. How it is going to be, sir? Now try to understand what this integration represent actually. This integration is done from t to t plus 2. That means what is the duration of integration? That means how much duration we are considering for the integration is nothing but 2 seconds. How? T to t plus 2. What is the duration? Which is nothing but 2 seconds only. Now we have to find out the area under a bounded function for 2 seconds. Will it ever become infinity? That's what the question. So it will never going to be infinity. Let's make a understand you. Suppose consider x of t. Consider x of t. Any signal which is a bounded signal. So bounded signal, I don't know. So its value will never go to infinity, but it is a bounded signal. Now I am doing the integration between t to t plus 2. T to t plus 2. That means the duration for the integration is 2 seconds only. The duration for the integration is 2 seconds. So whatever may be this area, whatever may be the signal from t to t plus 2, it doesn't matter, the area always a finite value. So because we are considering only 2 seconds, but here we are considering minus infinity to t, which is nothing but infinite duration. So here in this case it will never be considered infinite duration, we are considering only 2 seconds. So I can get this area is a finite value. So for a bounded input, the area under this curve from t to t plus 2 is a finite value. So I can say the system is stable. Okay, take it. Next, y of t is equal to integral minus infinity to t x of tau cos 3 tau d tau. So a system is defined like this. We have to examine whether it is a stable system or not. So to understand this, first we have to know one inequality called as squarge inequality. Squarge inequality. What the squarge inequality is saying? Suppose a signal y of t, which is integral f of t multiplied with g of t dt. So if a signal is defined like this, then if you try to find out the modulus of y of t, then what is this? This is the modulus, what we can say. This value is always less than or equal to, if I take this modulus inside the integration, that means mod f of t mod g of t dt. So this value is always less than or equal to. So there is an equality sign also. So this is called as Schwarz inequality. So now let's see. I am checking for mod y of t here, whether it is a bounded or not. We are checking. Is less than or equal to, from the Schwarz inequality I can write minus infinity to t mod x of tau mod cos 3 tau d tau. That's what it is. Now if I intentionally take these two signals maximum values, let's check it out. If I take the maximum values, whether the output is going to be bounded or not. If I check for the maximum values also. So let's assume the maximum value for x of t is equal to m. What is the maximum value of cos function? Always 1. These are the maximum values. Then this integration again less than or equal to m integral minus infinity to t d tau. So what is this integration value? T minus of minus infinity, which is going to be infinity. That means even though if you take the maximum values, you are getting this maximum value y of t maximum value is equal to infinity. That means the signal will become unbounded. So the system is unstable. Okay, take it. Next classification, what we are seeing is invertible and non-invertible systems. Invertible and non-invertible systems. Invertible and non-invertible systems. Now, so it is something like a function and inverse function. Okay. So let's say when a system is called as invertible system only when the system is having inverse system. I hope you understood. System, if it is having inverse system, then we can call the original system as a invertible system. Now here the doubt is, what do you mean by inverse system, sir? Suppose if a system is having inverse system, that means what is the characteristics of the inverse system? Okay, so first I am writing the definition. If the system is having inverse system, then the system is called as invertible system. Invertible system. Invertible system. Now, what do you mean by invertible system? If system and inverse system are cascaded, then the output is same as input. That's what the meaning of inverse system. What do you mean by that? Let's say if a system and its inverse system, this is a system and it is inverse system. If they get cascaded, if the input is x of t, then output has to be x of t. Then we can call this system is inverse system for the original system. That's what the meaning of it. Let's take one example you can understand easily. a system y of t is equal to root x of t. Root x of t. For this system, what is the inverse system? What is the inverse system? So inverse system has to be in such a way, if it is cascaded, we have to get the output which is same as input. That means, let's say, if input is x of t, what is the output of this first block? What this system will do? It will simply find the square root of the input. That means we are going to get output of the first block is equal to root x of t. Root x of t. If it is root x of t, what we have to do with this system? That means what is the operation done by this system so that I can get x of t? I can get x of t. I can simply say this is nothing but y of t is equal to x of t square. That means whatever the input, that has to be squared. So if root x of t is there, if I square it, I can get x of t. So I can say this system is inverse system. This system is inverse system. And this system is invertible system. Invertible system. If I ask other way around, you may get wrong answer. Let's see. What is that? If the system y of t is equal to x of t square, x of t square. For this system, what is the inverse system? What is the inverse system? Listen here. For root x of t, x square is the inverse system. You may think that for x square of t, root x of t is the inverse system, but that is not correct. Why? Suppose let's say y of t is equal to root x of t is the inverse system. Let's assume it is the inverse system. But whether it is inverse system or not, we will find out later. Let's assume for this system, it is an inverse system. Just I am assuming, but it may not be correct. Okay. Now, suppose if input is 3, what is the output? Square of the input, which is nothing but 9. What is the 9? What is the root of 9? Which is nothing but 3. Next, if I give input is minus 3, what is the output? Again 9. What is the output of the second block? That is also 3. That means for minus 3, we are getting the output which is nothing but 3. So I told you, for the input, we have to get the same output. So I can say this is not the inverse system. And first of all, it is non-invertible. Non-invertible. See, this is the one thing you have to remember. For this system, if it is an inverse system, it doesn't mean that for this system, this is going to be inverse system. There is no such thing like that. So you have to remember that, yes, for this system, this is the invertible system. That's the only thing we know. But for this, it may be, it may not be. We have to check further. Okay. Now, listen here. Sir, is it required every time we have to do this much of calculations and those things so that we can say it is a invertible or non-invertible? No required, not required at all. We can simply say whether the given system is invertible or not by checking one thing. What is that one thing is? For different inputs, 3 and minus 3 are different inputs. But what is the output we are getting? 9 and 9, which are nothing but same output. So whenever a system produces same output for different inputs, then it is non-invertible. That means every invertible system produces different outputs for different inputs. There is no such a thing which is going to produce the same output. If it is producing same outputs, we can simply say it is non-invertible. I hope you understood. So I am writing that point. Observation. What is the observation? An invertible system produces different outputs for different inputs for different inputs. So this is what we have to check, whether it is producing the same outputs or different outputs for different inputs. That's what we have to check to say whether it is invertible system or non-invertible system. Take it. Y of t is equal to mod x of t. Is it invertible or not? No, it is not invertible. Why? Suppose if I take x of t is equal to 3. What is the output I am going to get? 3. If x of t is equal to minus 3, what is the output I am going to get? Still 3. That means different inputs are producing different outputs. No, it is actually producing same output. I hope you understood. So different inputs are producing same output, then we can call the system is non-invertible. 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 Next. Y of t is equal to x of 2t. X of 2t. Is it invertible or not? Yes, it is invertible, because what the system is doing, simply compressing the signal. So by compressing the signal, two different signals cannot become same signals. I hope you understood. Two different signals cannot become same signals by compressing it. So it is a different signals are going to give you different outputs. So it is invertible. If it is invertible, we have to know what is the inverse system. Inverse system. What is the inverse system for this? So if I take y of t is equal to x of 2t, then what kind of system will make finally the output is x of t? That's what we have to check. That means if x of t is the input, what is the output of the first block? X of 2t. Then what we have to do this signal so that we can get x of t is the output. So what is the operation we have to perform now? That is nothing but expansion. That means y of t is equal to x of t by 2. So if I take x of t by 2, that means if I again expand this signal, I can get x of t. So that means in a continuous time case, first if you compress the signal, then expand, it won't make any difference. You are going to get finally x of t. So this is nothing but inverse system. Inverse system. Okay. In the similar manner, suppose if I take discrete time case, y of n is equal to x of 2n. We have to check whether it is invertible or not. So many people think that it is an invertible system because I can expand the signal, but it is not the case. Because it is a decimation, we will lose some information. So it is actually non-invertible. Why? I can prove it. Non-invertible. Suppose if I take the system which is y of n is equal to x of 2n. So which is nothing but decimation. Which is nothing but decimation. If the input is, let's say, x of n is equal to 1, 2, 3. Here is the arrow. What is the corresponding output if I do the decimation by 2? Y of n. Y of n. What it is going to be? So first what we have to do? We have to keep the 0th position as it is and pick every second sample. Then we are going to get the output is nothing but 1, 3. 1, 3. Now, if the input is x of n, which is equal to 1, 5, 3. Then what is the corresponding output? Here also what we have to do, keep the 0th position as it is and pick every second sample. Pick every second sample. So that is also going to give you 1, 3. That means different inputs are producing the same output or not. So if different inputs are producing the same output, so I can simply say the system is non-invertible. Okay, take it. Different inputs producing same output. Same outputs. Then we can say the system is non-invertible. Y of t is equal to e power minus mod x of t. Then y of t is bounded. Options: only when x of t is bounded. Option B: only when x of t is positive. X of t is positive. Option C: only when x of t is negative. Option D: even when x of t is unbounded. So which option is going to be correct? That means to become y of t bounded, what is the nature of x of t? That means, let's say, here the first condition, let's take out this only. When x of t is bounded, if x of t is bounded, is this function a bounded function? Yes. But here they have given only when x of t is bounded. So let's see next. When x of t is positive, then e power minus positive value. So definitely it is going to be always decreasing. So I can say this is going to be again a bounded function. Next, when x of t is negative, when x of t is negative, still it is going to be a positive value, e power minus some positive value. Suppose let's say e power minus 2 or e power minus 10, e power minus infinity also, still it is going to be 0. Okay, so I can say why I am not taking these three options, because of it is having only. That means this is the term which makes these options wrong. It can be positive, it can be negative, it can be bounded, even it can be unbounded. Why? Suppose if x of t is infinity, unbounded function, then still it is going to be e power minus infinity, the value is equal to 0. So this is the correct option. Even if x of t is unbounded, still y of t is a bounded function. Okay, take it. Suppose a input output waveforms are given for a system like this. and y of t is given like this. So we have to check whether it is a first option's linear, non-linear. Next, time invariant, time variant. Third one, static, dynamic. Fourth one, causal, non-causal. Next, fifth one, stable or unstable. Stable or unstable. Next, invertible or non-invertible. These things we have to examine. These things what we have to examine. So to examine anything, what we require is what is the input output relation. What is the input output relation? Let's say first try to understand. Input x of t, we got output y of t. Now if you observe carefully, input output relation y of t in terms of x of t. Here the duration of the signal is 2 seconds. Here also the duration of the signal is 2 seconds. That means there is no scaling factor. Time scaling factor is not there. Next, the amplitude is 2 here, the amplitude is 6 here. That means there is a amplitude scaling factor of 3. Next, the signal is simply shifted here by 2 seconds in the right side direction, means the signal got delayed by 2 seconds. So in simple, I can write y of t is equal to 3x of t minus 2. That's what the input output relation. So you tell me, is it a linear relation or non-linear relation? Yes, it is y is equal to mx. So I can say it is a linear relation. Is it a time invariant or time variant? It is time invariant. Is it static or dynamic? It is dynamic. Why? Suppose if I try to find out y of t1, it is x of t1 minus 2. So definitely it is depending on the past value. So it is dynamic. Causal, non-causal, it is a causal. Why? It is not depending on the future values. It is depending only on the past values. Next, stable or unstable, it is a stable system. Why? Because if x of t is a bounded, x of t minus 2 is also bounded. If it is bounded, if it is multiplied with some 3, still it is going to be bounded function. So that is a stable system. Invertible, non-invertible. So it is an invertible system. Why? If I take the same signal, multiply with 1 by 3, and if I advance the signal by 2 units. That means, let's say, if I take the system like this, y of t is equal to 3x of t minus 2. Tx of, I'm just taking here, y of t is equal to 3x of t minus 2. For this system, what is the inverse system? Which is nothing but y of t is equal to 1 by 3 x of t plus 2. That means we have to advance the signal. Then we can say the system is inverse system. This is an invertible system. Clear? Take it.